Yeah, it is working now. Okay, cool. Sorry about that. Had some minor connection issues apparently. Twitch decided to make me re-enter my account stuff. Okay. But that aside, let's go ahead and get going then. So last time we did yet more unit conversions, um, you know, endlessly over and over again, because it's a very important skill for us to have. So we're going to continue doing that today for a little bit, and then we will start moving forward with our next chapter, which will be talking about atoms. So here is another kind of special case of using a kind of physical property as a conversion factor. Oops. And this particular one is called the specific heat capacity. And this is technically defined as, I mean, you don't need to memorize this definition. Good morning, Lisa. What was I saying? Oh, yes. It's the energy required to change the temperature of 1 gram of a substance by 1 degrees Celsius. Relax, creature. So we're going to see there that it's going to take the units of, by the way, it's abbreviated C. That's what specific heat capacity's letter is if you want to use it in an equation. But C will take the unit of joules per gram degrees Celsius, or joules per gram Kelvin. Either way. We're going to see that both of these will be exactly the same unit, so we don't have to worry about that. Believe it or not, these two are the same unit for this particular factor here. So, if we want to kind of dissect the units of this, I'm just going to actually copy the units again before we mess with what they all mean. So, on top there is joules. Joules is a unit of energy, which is given the abbreviated letter of Q for some reason. Degrees Celsius, of course, is a measure of temperature. But notice since our definition actually talks about changing the temperature, this is going to be a temperature change. So since we're talking about how much energy to change the temperature of something, we're dealing with temperature change for this. And of course, this is just a mass here. So oftentimes, we're going to see that mass is abbreviated with M, and temperature change is going to be what's called delta T. Delta in chemistry means change in, which means whatever it is, your final value of it minus your initial value. So for delta T, that means your final temperature minus your initial temperature. So if we're talking about, heating something up, we're going to have our our final temperature be higher than the initial temperature. If we're cooling it down, we're going to have the final temperature be lower than the initial temperature. So it's just kind of a way of talking about this change in that particular property. And so we're going to see that specific heat capacity will be essentially a conversion factor telling us kind of how to throw some quantities together in order to make this work. So remember that the specific heat capacity is going to be in those units. And that's going to tell us a formula if we want, if we are formula inclined. That's going to tell us, if we just look at those units, that we have Q over M times delta T. Just putting those units in. So we have our energy term, our mass term, and our change in temperature. And now oftentimes people don't like to have equations with all these fractions in them. So you'll often see this kind of rewritten like this. And people sometimes call this the MCAT formula because that's what it looks like, right? So if any of you are considering medicine, the MCAT, of course, is what you're going to take before med school. So people will often kind of call it that. So what we can see here is we were able to take kind of the units of a constant or a conversion factor and throw together a formula. So just like yesterday, we talked about density having units of grams per milliliter. That's the units of a mass and a volume. That's what density is equal to, right? Just by looking at the units of it. So we're going to be able to kind of mess with this. So if you like to use it as a conversion factor, go right ahead. If you'd like to use it in equation form, go right ahead. It does not matter to me. It'll work either way. So let's kind of put this in context here. So let's say that I'm going to, if I give, let's say 125 grams of water, let's say I'm going to give it 8,000 joules of energy. Actually, let me, no, it'll be okay. Let's see, and it starts at 20 degrees Celsius. What is the final temperature? And I'm going to give us the specific heat capacity for water is 4.184 joules per gram degrees Celsius. So this is kind of a typical, standard problem in chemistry where you would be given a bunch of various values and you're asked for one particular quantity. So if we want to use our happy formula, I'll copy it again for us here. Let's go ahead and try and take parts of this word problem out to see what quantities those represent. So in this paragraph here, it looks like I have 3 different numbers. So let's go ahead and see what those numbers represent. So remember our formula, Q represents energy, M is mass, delta T is change in temp, and C is the heat capacity. So let's go ahead and see if we can't take all these numbers out and assign them one of these letters. So going just as if we were reading this paragraph, our first number is 125 grams. Looking at the kind of 4 options we have here, grams is a unit of mass, right? So that tells us, that this is our mass. 125 grams, just by looking at the units of that particular quantity. The next number we have is 8,000. That's with 4 sig figs, by the way. There's a decimal there. And that unit of that is joules. Joules is a unit of energy, right? So that tells us that that number is Q. And then our final number, it says it starts at 20 degrees Celsius. And that, therefore, is going to be our initial temperature. Our initial temperature is going to be 20 degrees Celsius. And of course, we're already given the C for water, so we don't have to worry about that. So we now know we have M, Q, temperature initial, and C. Therefore, we can solve for the final temperature. Remember that delta T is the same thing as final minus initial. If we were to just replace delta T with what it means. So, if we are going to solve this equation, whenever you're solving equations, again, you have kind of two roads to go through. You can either just throw in all your numbers and then solve for the variable at the end, or you can solve for the variable first and then plug in your numbers. Either way will work. If you do solve for the final temperature, you get Q over MC plus the initial temperature. So if you want to do it that way, you're welcome to. You can just plug stuff into this first one. It'll work. So let's go ahead and do that. So it looks like we had 8,000 joules to start as our Q. So 8,000 joules was 125 grams. That's M. C is 4.184 joules per gram degrees Celsius. May make that other parenthesis a little bigger. And then we have our mystery variable, which is the final temperature, minus 20 degrees Celsius. So if we really wanted to do all this stuff, we can go ahead and do it. I assume you guys can solve this equation on your own. So let's go ahead and do it. So we have 8,000 divided by 125 divided by 4.184 plus 20. And it looks like if you solve this equation, you get that the final temperature is going to be, oh gosh, we have to worry about sig figs. Always sig figs are troublesome, right? If you go ahead and do all this fun stuff, notice that we're going to have it in kind of this multiplication division term. Should not be 4.7 because we're starting at 20, we're giving it heat. So double check your answer there. Technically, we should do our sig figs there. We should have 3 sig figs overall for this component, and then we have 1 decimal point for the initial temperature component. So we're going to want to take a number with 3 sig figs and add it to 20 degrees, and I think we do get that. We get 15.296 plus 20. This number has 3 sig figs, so putting that all together, you get 35.3 degrees Celsius. Yeah, that's what I get as well. It's always a good thing when you, as the listeners, get the same thing that I do. So, Tedward, I would go ahead and double check your math or something, just to make sure. Cool. So we could figure out what to do with temperature here. Notice this is an equation of 4 terms wherever it went. There it is. Or technically 5 terms. Well, I mean, we're not going to necessarily do more practice right now with it. This is something we're going to deal with a lot more in chapter 8. No, 6. Somewhere around there, we'll deal with this equation quite a bit more. But for right now, dealing with this energy stuff, you can just do it for some of your homework problems, or you can use the textbook problems for more kind of practice with it. But suffice it to say, you should be comfortable to solve for any variable in a formula given all the others. So that's something you're going to want to be comfortable with. So notice in this case we have MC delta T. I could ask you to solve for any one of these. So you should be able to be given the others 3 and figure out what the 4th one is. So that's what I'm saying here. So we have 4 terms, 5 terms if you really want to think about the temperature, but whatever. Given 3, you can solve for the last one. So something to think about. All right. So definitely make sure you're able to do that. If not, you may want to just YouTube just solving equations or something, or Google it. But that's definitely a skill you're going to need. So cool. All right. Any questions on that thing? So just another, fun application of chemistry for us. Okay. Well, in that case, let's start talking about atoms. So you do have a dimensional analysis homework problem. It's up on Canvas. It's due this Sunday. That'll be there. I'm probably going to give you one on atoms as well, so you'll have 2 worksheets this week. The atoms one, don't worry, is actually pretty short. Oh, look at my doggies. They're all kind of lumped together over there. 3 of them just squashed up against each other. It's pretty cute. If they're still there, I'll take a picture and upload it for you guys. But now let's actually start kind of moving away from just general, math things and to actually start talking about chemistry. So with that, of course, if there's any questions, throw them up there. We'll go over them. But for now, we'll just keep on chugging. So atoms is going to basically cover chapters 3A, 3B, and 4. But we're going to start with 3A. So we're just going to kind of, deal with kind of basic structure of an atom. So first, I guess we kind of have to define what an atom is, right? And so we're going to see that an atom is the smallest kind of unit of matter that I've kind of ruined the grammar of this definition. I'm totally putting this in passive voice. That can be kind of isolated. Cool. I'm glad you found out where the problem was. Oh god, let's just say that. Be isolated. It's kind of the smallest bit of matter that if you were to just take a piece of something and just keep breaking it breaking it in half, breaking it in half, breaking it in half. Eventually, you'd be left with one atom, and that's where you would not be able to break it anymore. So we generally say that atoms cannot be divided further. Though, of course, in nuclear chemistry you can. But this is a definition that comes from, the Greeks 2,000 years ago or whatever, where they definitely did not have access to nuclear fission at the time. So basically, the atom was defined as kind of the smallest unit of matter that you can have. Nowadays, though, we know that atoms are made of 3 components, which we call subatomic particles. And those 3 particles are going to be the proton, the neutron, and the electron. So we're going to have our 3 subatomic particles here. You've probably heard about them. You probably know what they are. This is probably going to be just a review for you, but that's okay. We're going to go over them anyways. So we have 3 subatomic particles here that are going to make up our atoms. And let's just go ahead and kind of compare them. We're going to see that there's going to be some kind of quantities we can talk about relating to these particular particles. And let's see, how about location? We can talk about these things. So charge of these particles, we're going to say that the proton is defined as the one being positively charged, a +1 charge. A neutron will have no charge, and an electron will have a charge of -1. So protons are positives, electrons are negatives, and neutrons are neither. They are neutral, hence neutron. We're going to say that the mass of a proton is 1 atomic mass unit, or roughly 1 atomic mass unit. A neutron will be the same. Neutron is actually a little bit heavier, but we don't need to worry about that right now. And an electron is about 1/2000th the mass of a proton or neutron. So much, much smaller in terms of mass. So there we have it. And then finally, in terms of location, the protons and neutrons are going to be located in what's called the nucleus of an atom, whereas electrons are going to be orbiting the atom. Ooh, what gives them their charge? Oh gosh. So you're going to go into particle physics here. It's the arrangement of the quarks that make them up that give them their charge. So I am not a physicist. I can't necessarily tell you where charge comes from, but it is the arrangement of how these particles are kind of put together. So subatomic particles are made of quarks, muons and hadrons and all these sort of fun little terms there. And just how they're arranged, the quarks can determine what the charge or something is going to be, as well as its mass. Bit too advanced for me, but suffice it to say, you definitely don't need to know that. But that would be a fun question for Google, perhaps. Or just go to Wikipedia and talk about particle physics here. And that's you can have fun doing that. So, cool. Anyways, so let's kind of look at it in, a way you've perhaps seen it before. Generally speaking, you have a dot in the center, and you've got some stuff around. where this dot is going to represent your nucleus, and the blue thing is going to be kind of electron orbits. We are going to talk about better ways of describing atoms than this, but this is kind of the generic preschool way of describing atoms, right? You have got a nucleus and you've got these orbitals, and there you go, you've got rings around the nucleus, and hooray, there you have an atom. We're going to see we have many more sophisticated ways of talking about atoms that are more like mathematically correct. But suffice it to say, you have a nucleus and you have electrons kind of zipping around throughout there. I don't know, I'm just going to put some electrons in there. So, a couple things to note, that the nucleus is incredibly small compared to the overall atom. So consider that, if I remember correctly, I don't know, 10 to the 14th of an atom is empty space. Atoms are mostly emptiness. Yeah, you can think of them as clouds, though we're going to see that we have very specific clouds come chapter 4. So roughly, if we're looking at percentage-wise, this is, the actual nucleus and electrons of an atom take up, let's see, 1 over 10 to the 12. We'll talk about valence electrons as well, but that'll be chapter 5. Actually, no, we will talk about valence electrons in chapter 4 a bit. So suffice it to say that if you want to think of an atom, think about like Dodger Stadium or something. I'm sorry, I'm from LA. So if you want to think an atom, if an atom is the size of Dodger Stadium, the nucleus of an atom is 1 grain of sand in the pitcher's mound or something. So your nucleus is going to be just 1 little grain of sand, but your atom is the entire stadium. So the nucleus is very, very, very small compared to the size of the atom. However, what's interesting is that the nucleus has almost all the mass of the atom. So, we're going to see that 1 grain of sand has all the mass. There's some slight amount, around in the stadium, but that 1 grain is going to have all the mass. So it's pretty remarkable. So let's go ahead and look at these particles a little bit more. We're going to see that we have a couple more kind of terms to go over here. And then we'll get into like actually looking at atoms. So atoms tell us a kind of bunch of information. The first thing, kind of definition that we want to deal with is that of an element. Let's just say element, singular. An element is defined as it has something that has atoms of the same type. And that's kind of a vague definition. But we're going to see that elements are going to have atoms that are all going to be the same type. Meaning that a chunk of sulfur as an element is made entirely of sulfur atoms. The atoms are of the same type. We're going to see there's some other flavors that we can mess with. But suffice it to say that this means we're actually talking about the number of protons. So each atom of a particular element, I don't know how to spell, element, have the same number of protons. That is how we're going to define an element. So every, sulfur atom would have 16 protons. And that is not something that can change. So as soon as you that number is not 16, you have a different element. If it's going to be sulfur, it has to have 16 protons. Another example: a hydrogen atom will have 1 proton. Not more, not less. Must have 1 proton. We're going to see that we call this number the atomic number, which of course is given the abbreviation Z, because why not? That is going to be our number of protons. And we're going to see that the periodic table is organized by your atomic number. So let me just flip over to, I'm pretty sure I have a periodic table on this thing. Aha! So I do. If you notice here, this is what the periodic table looks like. We'll be dealing with this more probably chapter 5, but this is what it looks like. It's going to be your best friend throughout the semester. Notice that in the kind of top left corner of all of these elements, we have a number. Notice that hydrogen has the number 1 in its top left corner. And if we look at sulfur, which is over here, hopefully you can see me like circling that. Sulfur, notice it has the atomic number of 16. So that tells us that sulfur atom will have 16 protons. And for example, if we were to look at nitrogen, we would say, okay, every single nitrogen atom has 7 protons. And so we're going to be able to kind of identify different elements by their number of protons. So cool. And if we wanted to figure out how many that was, we would just look on the periodic table. We'd find whatever element I'm asking you for, and we would know, here, let's do it. How many protons does neon have? If that is a question for us, we zip over to a periodic table, and we're going to try and find neon on this. So, just for your own reference, I would definitely find some periodic table online and print it out or something. Or the textbook has one as well that kind of pops out. It would definitely be a good idea, just so you'll be able to reference this pretty often. Aha! And here's neon. I have found it. And it has the number 10 in the top left corner, which tells us that neon has 10 protons. We would just find that from the periodic table. We got it from the periodic table. Hooray! Alrighty, questions on protons. Alrighty, it turns out atoms of the same element can have different numbers of neutrons. Allow me to do a couple of drawings here. Okay. Okay, so here's my lovely drawings here, where blue is going to represent the neutrons. Let's say that all of these have one proton in them, which tells us they're all going to be hydrogen, right? They all have one proton. They're all hydrogen atoms. We're going to see that in this case we have 0 neutrons. In this case we have 1 neutron. And in this case we have 2 neutrons. If we go back to that kind of table that we had at the start, we saw that both protons and neutrons weighed about 1 atomic mass unit. And so we're going to see that these atoms will actually have different masses as a result. We're going to see that this particular atom on the left will have 1 AMU total for its mass. This one will have 2 atomic mass units. And this one will have 3 atomic mass units. These would be the kind of mass of the atom here. And so, even though these are all the same type of atom, they're all hydrogen atoms, they have different masses. And so, we have a term for this. We're going to say that these are called isotopes, where it's the same element but different mass. And so that just means that we have a different number of neutrons within our particular atom. So we talk about this by saying, for example, hydrogen 2 to indicate its mass number. We're going to see what mass number is. We would call this one an atom of hydrogen 3. And of course, that first one would be hydrogen 1. So we're going to see here we have something called the mass number. That's going to be abbreviated with an A, by the way. Oops. You know what's really... Yeah. So, let's talk about that in a second. The mass number is going to be your number of protons plus your number of neutrons. So they're roughly the same mass. So the total of those will tell you kind of how much mass you have. So let's talk about neutrons. So neutrons are there for one reason. You may realize that in an atom with 16 protons, you have 16 positively charged things very, very, very close together. And as you may know, positive charges would repel other positive charges, right? We only see attraction between opposite charges. The neutrons actually generate what's called a strong force. So in physics, there are 4 forces, right? You have gravity, You have electrostatics, you have a weak force, and a strong force. We have 4 forces in physics only. The strong force is so strong that it is able to keep these positive things stuck together, despite the fact that the things are positively charged. They don't want to be together. So the strong force can overcome the electrostatic repulsion there. So more neutrons can mean more stability, because neutrons are going to be what's helping those protons to stay together. Though we're going to see that every atom will have its own kind of preferences for how many neutrons it wants. For example, here, let's go to our dear friend Wikipedia. Let me pull open Chrome here. Okay. Let me pop this window open. Okay. Let's take, how about silver? Here is an element. Aha. Here are some isotopes of silver down here. We're going to see these are the mass numbers, kind of written up here. Here, let me zoom this in, just so we can see it all. We see all of these isotopes of silver are going to have different numbers of neutrons. What's written here, something that we're not going to really talk about in this course, is half-life. It's a measure of how stable these are. So we're going to see that it turns out that this silver has 2 kind of stable isotopes. So numbers of neutrons that kind of make it happy. We see that if it has a mass number of 107, it's stable. But if we take away 1 neutron, it kind of breaks down pretty rapidly. Breaks down within days. If we add 1 neutron, it lasts for 400 years. A little bit, interesting. But we're going to see that adding 2 neutrons makes it stable again. So, and then, adding more than that will mess it up. And so if we look at another element, let's say, how about cobalt? I don't know, just making some of these up. Cobalt only has 1 particular number of neutrons that makes it stable. The rest of them are radioactive. And so it just, it varies atom to atom. So some of them, here, let's look at arsenic. Why not? Same idea here. In this case, again, we only have 1 particular stable isotope of it. I want to try to find something that has a lot of stable isotopes. How about platinum? Let's see. I think platinum had a bunch. Yeah. So platinum has a whole bunch of them that are stable and that are going to have different, numbers of neutrons. So, and then go ahead, look at number 193. That's the one that doesn't last very long. Go figure. There's some very fancy reasons, I'm sure, that deal with particle physics as to why that number is not particularly stable. But suffice it to say that it just varies atom to atom. So, I'll just put that as a footnote. Each element, I guess I should say, not atom, has a kind of preference for mass number. So there we go. I'm glad we're learning something. Cool. So suffice it to say that there will only be certain isotopes of any given element. And so we're going to see that some of those isotopes are much more favored than others. We'll talk about that in 3B. But for right now, we're just kind of doing definitions. We often will, let's mess with electrons first. And then we'll come back to this. So electrons are kind of special for us. They are able to move between atoms. we're going to see that most of the chemistry we talk about, 99 some odd percent, deals with electrons moving around. That's what chemical reactions are all about. We're going to see that life exists because electrons can move around. So, very important kind of component here. And so, if an electron leaves an atom, the atom becomes positively charged overall. So protons and electrons have the same charge, but different sign, right? Proton is +1, electron is -1. So if you lose an electron, if it has left to go to a different atom, you're left with an extra positive. So normally we're going to see that elements will have the same number of protons and neutrons. However, electrons. If we mess with that number of electrons, we're going to end up messing with the charge of our atom overall. We're going to see that conversely, if an electron comes to an atom, the atom becomes overall negative. So, here we go. Here is magnesium. Magnesium normally has (12) protons and 12 electrons. We're going to see here that the charge of a particular atom is going to be the number of protons minus the number of electrons. In this case, we have 0 charge. It's neutral. If we lose an electron, we now have 12 protons minus 11 electrons, which equals a positive charge. If we instead let's say we've gained 2 electrons, and that would bring us up to 14. The charge would be 12 minus 14, which is -2. So we're going to see that the charge of your atom is going to be determined by the number of electrons you have. And electrons are kind of mobile, so they can leave, they can arrive from a different atom or something, and so we can end up having charged species as well. Charged atoms are called ions. And specifically, we kind of have 2 types. Positive ions are called cations. Not cations, but cations. Negative ones in purple, why not? Are called anions. We typically will write the charge of an atom in the top right. So, for example, we had a magnesium plus ion. And then the second one, where it had gained 2 electrons, we had a one with a charge of -2. What's bizarre is chemists will talk about the charge in the opposite way than normal mathematicians do. Like normally, you'd have -2, but we talk about that as 2 minus. For whatever reason, we put the number first and then the sign. So let it be known. Some biologists will actually write the minus twice. They'll write Mg minus minus, for example, if this were the case. Magnesium doesn't really ever form negative ions, but that's okay. We're just doing, generic stuff right now. So just so you know, we will be writing the number first and then the sign. The charge is written number and then positive or negative. For example, aluminum 3 plus, phosphorus 3 minus, carbon 4 minus, fluorine minus, whatever. So we're going to see that we always write the number first and then the charge. Alrighty. So let's kind of summarize here. So if we change the number of protons, we change the element. This is kind of a summary of all the things we've talked about. So the number of protons determines the element you are. So if you change that number somehow, you're a different element now. So let that be known. If you change the number of neutrons, you change the mass number. Which is, remember, protons plus neutrons. And we call that an isotope. Technically, this would also be changing the atomic number. And if we change the number of electrons, we change the charge. Remember, charge is going to be equal to protons minus electrons. And then we call those ions. All right, and remember that you can have two kinds. You can have cations. I don't know what colors I'm using anymore. And anions are negative. So we kind of have two flavors there. All right, so that's kind of the essence of chapter 3a. Honestly, it's a very short chapter. We'll be talking about how to figure out the numbers of all of these things with some examples tomorrow. We'll start on that. Before I let you go, though, do we have an exam next week? Let's find out. 101, let's see. We may have an exam next week, in which case, let's see, 280. Yeah, we do. So your exam next week, the syllabus says it covers 1 through 3b. It'll cover as far as we go tomorrow. So we may start 3b, we may not, just depends. We'll just see how far we get. We'll talk about the exam more tomorrow, I suppose. And then on Thursday, what we'll do is we'll have a review. So how that's going to work is you'll just bring me questions. say, hey, can we talk about this isotope stuff again? I don't understand it or whatever. Try, of course, to be as specific as possible, but yeah, we'll have an area where you can write questions in, and on Thursday we'll go over them. So we'll start getting that together. I think I have practice exams on Canvas, although they maybe fill in. No, actually, I think I have both kinds, as well as their keys. Just understand that those are from different semesters, so maybe that semester I had covered more in this given amount of time, or maybe I covered less. So, if something is like, hey, what the heck, we never covered this, it's not going to be on the exam then because we haven't covered it. So, just understand that. Your exams are going to be multiple choice through Canvas, so they're just going to be like a little quiz thing that you'll take, and it'll just have, it'll be open book and all that stuff because I have no way of controlling that. We don't have Proctorio anymore, so it's just going to be open universe, I guess. So everyone's going to do well. That's my hope. So, yeah, but we'll talk about that more tomorrow. I will put another worksheet up for atoms later today. So double check that. That's also going to be due Sunday because that's when your exam is, or rather the day before your exam. And I want you to be able to make sure you have practice with those. So with that, I'll see you all tomorrow. Take care.